Hello, this is Dr. Zach. So today we are going to determine the difference between secant lines and tangent lines, to tell the difference between average rate of change and instantaneous rate of change, and to start using the derivative notation correctly. So with all that in mind, let's get started, please. As we're looking at the slope of the secant line, that's going to measure the average rate of change or your average velocity. We have some slope formulas that we need to know. And as we look at the graph, the slope of the secant line is the blue line that's drawn in this picture connecting two dots. The change in x is the difference in the x values as you go across. Change in y would be your function evaluated at c plus delta x minus f at c. And now let's take a look at our first example when we think about these problems. Come on, move the screen. All right, so for example 1, we're looking for the average rate of change. Now, as you do each problem, for any problem that you set up, I want to see the formula. So average rate of change is going to be f at 5 minus f at -1 divided by 5 minus -1. Next, we're going to substitute the 5 into function f of x, and that gives us 1 over 5 plus 2 minus 1 over -1 plus 2, all divided by 6. So this will give us a 1 over 7 minus, that just simplifies as 1 all over 6. You can use a calculator if you need to. If you don't need one, remember, just find your LCD. So this is 1 minus 7 over 7, all divided by 6. But you've been practicing with those delta x's. You know the 6 is just going to be in your denominator. -6 over 6 times 7, which is -1 over 7. So this is your average rate of change, or the slope of your secant line. Now we're going to do an application problem. In this problem, we have a ball that's dropped from a height of 100 feet. The ball's height at time t is given by that position function. So this is our first time that we're looking at s of t, and s of t, as I told you in the notes, is considered height. This is going to be equal to -16t squared plus 100. Now, these other ideas are important. S of t is measured in feet. T is measured in seconds, and we're looking for the average velocity over each of the time intervals. So if we want the average velocity, that's going to be s at 2 minus s at 1 over 2 minus 1. This is going to be equal to, now we substitute our 2 in, -16 times 4 plus 100 divided by 1. So we have -64 plus 100, which is going to be a nice positive 36. All right, now the units we're playing in, that's why these became important. The distance in the numerator was feet. So this is 36 feet, and the time is in seconds, so it's feet per second. So the average velocity is 36 feet per second.
Square it.
Now let's go back one more time. It wasn't just the square. This first part is s of 2, isn't it? Did I put in s at 1? I didn't, did I? So if I put in s at 1, that's going to be -16 plus 100, and -16 plus 100 is going to be another 84. So we have -64 plus 100 minus our 84 divided by the 1. Ooh, so I'm off. So Tommy, if I now subtract my 84 feet per second, because I forgot the second part of the problem, What is my new velocity, Tommy?
Negative 48 feet per second.
And that's why you're telling me the ball was heading downward, isn't it?
Yes.
All right. So the negative tells me that the ball heads downward. And if it's a positive, then the ball would be heading upward. All right, so average velocity uses the slope formula. I'd like you to take a moment now, please, and complete question B on your own. That should take you maybe 2 minutes, and then we'll have Frank share his answer. So Frank, when you're ready, drop the answer into the chat for everyone to see, okay? So for example 3, as we look at instantaneous rate of change at 4, now in the picture that I've provided on the right-hand side of your page, what you should notice is the tangent line is getting closer and closer to the point from each one of these pictures. Now, because we're blowing up our pictures, do you see how it's shrinking here? What's happening to that delta x as we get closer and closer to our tangent line? So, Catherine, the tangent line, what is happening to the delta x as we get closer and closer to the point?
Isn't it approaching 0?
Yes, that's perfect. So Catherine said delta x is approaching 0, and she's absolutely right. So when we take a look at the slope of the tangent line, we're going to use the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, which is just like the problems we were working on yesterday, where we have A approaching B. So if A is approaching B, then the difference between A and B is going to 0. So the second equation is another way to look for instantaneous rate of change, or the velocity at one point. Now, once again, a velocity problem at one point is going to be a measure of meters per second, or it's going to be a measure of feet per second. And that's why we're going to have some sort of height or position for s of t, for s, so that we can find its velocity. All right, so let's take a look at our first problem. We have f of x equals 1 over x plus 2. Find an instantaneous rate of change at 4. Now, there are a couple of ways to do this problem. I'm going to go with the one that's probably most familiar at this point. If I'm finding the limit as delta x goes to 0, f of x plus delta x minus f of x divided by delta x. Now, you've worked with me long enough, you know that I'm going to expect you to write the formula and then apply the formula. So here's my formula. The next thing we want to do is figure out f of x plus delta x. And we're going to put x plus delta x in for the x value in my function. That leaves me with the limit as delta x goes to 0, 1 over x plus delta x plus 2 minus 1 over x plus 2, all divided by delta x. So the first thing that we've done is we have accomplished substitution. Notice I didn't even use the 4 yet. I'll deal with the 4 at the end of my problem. Okay, so next I'm going to write the limit as delta x goes to 0. So this problem looks like an LCD problem that we practiced in Unit 1. So we're going to cross multiply in order to find common denominators. We get x plus 2 minus the quantity x plus delta x plus 2, all divided by, all right, now this is where that practice came in. That was so nice. We have x plus delta x plus 2. x plus 2. And we know from prior experience, delta x goes in the denominator. All right, I'm going to pause here and see if you have some questions. Okay, so now that we have all the substitution, we want to simplify the numerator next. When we simplify the numerator, keep your limit. Delta x goes to 0. X plus 2, distribute the negative. There's negative x, negative delta x, negative 2. I haven't done anything yet with my denominator. It just follows along. So we still have the denominator. All right, now I'm going to simplify, and hopefully I'm going to get the same thing that Alex had. The x's will cancel.
No, mine's not gonna be the same.
Oh, it's not? What did you do differently? Where was your
I think I messed up the top.
the top? Okay. Did you forget to distribute a negative?
Yeah.
Okay. Very common, so now you know to keep an eye out for it. All right, I have a delta x, negative delta x, over the quantity x plus delta x plus 2 times x plus 2 delta x. Okay, now, do you see how the delta x's are going to cancel? All right, Sophie, I'm going to give you a warning. If your delta x's don't cancel, one in the numerator, one in the denominator, somewhere you have made a small error and you need to go back and find it, okay? All right, so I'm canceling out my delta x's. I'm keeping the limit notation. I'm obsessed with that. We have a limit as delta x goes to 0. I think I'm writing off the board. So let me go up here. The limit as delta x goes to 0. We're left with negative 1 over x plus delta x plus 2, x plus 2. All right, and the next step in our process is to let the delta x go to 0. We have negative 1 over x plus 2 times x plus 2. All right, now this is the instantaneous rate of change. I'm going to give you some new notation because writing instantaneous rate of change over and over and over again, what a pain. F prime of x is new notation for you, and it means find the instantaneous rate of change. Look at that. All those letters, find the instantaneous rate of change, are represented by f prime of x. Okay, Lauren Pyth, do you know another name for f prime of x?
What do you mean? Like, what do you?
Well, it's new notation, I know that, but do you know another? Have you ever seen it before? Like running around in a field and like, oh, there's an f prime of x. Have you ever seen it before?
Like in another area of math?
Yeah.
Yes. I forget. Like, I can't pinpoint it.
You don't remember? Okay, that's fine because I haven't taught this, so it's not what I expect. Debbie, do you know another name for f prime of x?
Nope.
No? Anybody?
Isn't it the derivative?
Yes! This is the derivative. Okay, so that's your derivative, which is very cool. Now, we didn't answer the question. I want to find an instantaneous rate of change at x equals 4. So what I'm looking for is f prime at 4. And I substitute in my 4. I get negative 1 over 4 plus 2, quantity squared, which is negative 1 over 36. So the instantaneous rate of change at x equals 4 is negative 1 over 36. Okay, so we're told to find the slope of the tangent line to the graph at x equals 4. But isn't slope of the tangent line just another way to say instantaneous rate of change? So then the answer for the slope of the tangent line is -1/36. And then find a derivative at x equals 4. Well, the derivative is the slope of the tangent line, which is the instantaneous rate of change. So the answer is -1/36. Now, write an equation of a tangent line. So this one we haven't done this year. If I want the equation of a tangent line, let's think about the equation of any line. Now, some of you have been using y equals mx plus b. I'm going to ask you to use y minus y1 equals m times x minus x1. So this is the equation of a line that I prefer you use when you work. So the slope of the tangent line is the instantaneous rate of change. So that's -1/36. I know that x equals 4. What I don't know is the y value. But in the original problem, f of x was equal to 1/x plus 2, wasn't it? I can't see it now. So if we know f of x is 1/x plus 2, to find the y would equal f at 4, which is 1/6. Now I'm going to substitute y minus 1/6 equals the slope, and the slope is -1/36 times x minus 4. And we can actually stop right here unless the directions tell you to write it in a different form. The formula that I have written right here is an estimate of your velocity, because as you look at it, you can see that it takes the form of your slope equation. So we're looking for the velocity at 3. That's going to be, these little wiggles mean approximately equal to s. Now the t value that you were given was 3. So we're going to put in 3.001 minus s at 3, all divided by 0.001. So this is a substitution problem. You know that s of t is the square root of 3 minus t. So to solve this problem, my suggestion is, in your calculator, let y1 equal the square root of 4 minus t. Then you can use a table of values to figure out s at 3.001 and an s at 3 divided by 0.001. So how you use your calculator is up to you, but at this point, grab those calculators, figure out what the approximate velocity is going to be. So please get the calculator going. All right, so we're going to go with -0.5 as the answer to this problem. And now let's look at example 5. Looking for the slope of the tangent line to the graph, f of x equals x squared minus 2. And then I want to write the equation of the tangent line at x equals 2. So there are two parts to this problem. So let's start with the slope of the tangent line. The slope of the tangent line is equal to the limit as delta x goes to 0, f of x plus delta x minus f of x, all divided by delta x.
Dr. Zach, I have a quick question about the last one.
Once you have your definition, now we do our substitution. And remember again, substitutions where sometimes we want to think carefully. The x's are going to be substituted. So I have two parts for this one. We now get the limit as delta x goes to 0, quantity x plus delta x squared minus x plus delta x. So this blue part are the replacements I made for the variable x. Minus f of x, use parentheses. We have x squared minus x. And that's all divided by delta x. So now we're going to multiply this out. We get the limit as delta x goes to 0, x squared plus 2x delta x plus delta x squared. So that's all of that first term. Minus x minus delta x minus x squared plus x. All divided by delta x. All right, now let's see what cancels. X squareds are out of here. X's are out of here. And now what remains is the limit as delta x goes to 0, 2x delta x plus delta x squared minus delta x all over delta x. All right, Mary Rose, can we factor out a delta x?
Yes.
All right, so we're going to factor it. And if we can factor one out, we're right on track. 2x plus delta x minus 1, don't lose that 1, divided by delta x. Now, here's the good news. All derivatives are based on limit notations. But once we do enough of these, we're going to find patterns so we won't have to use the limits anymore. So don't worry. We've got 1 or 2 days of practicing with limits, and then we're going to find some shortcuts. Okay, David? Now, yeah, because we definitely want some shortcuts. We have the limit now, delta x goes to 0, and our answer is 2x minus 1. All right, just to practice that notation we were talking about, f prime of x must equal 2x minus 1. All right, you guys, we're going to take a pause. So now I know that f prime of x is 2x minus 1. That's your derivative, which is how I find the slope of my tangent line. So if I'm looking for the slope at x equals 2, then we're going to find f prime at 2, which is 2 times 2 minus 1, or 3. So 3 is a slope of the tangent line. Here's some new notation for you, Matt Kinzel. When x equals 2. So this little line is a new math word for when or at x equals 2. Okay? Now, since I'm writing my equation, I will write my formula, y minus y1 equals m times x minus x1. I know x is 2. I know my slope is 3. I am missing the y value again. Y equals f at 2, and f at 2 is 4 minus 2, which is 2. So now I fill everything in. Y minus 2 is equal to the slope times x minus 2, and this is the equation of my tangent line. All right.